Welcome to this presentation. I would like to talk to you about supply chain optimization under demand uncertainty. And in particular, I would like to talk about the so-called single echelon approach versus the multi-echelon approach. The single echelon approach is the one that we have been using ever since inventory theory started, which you can situate since 1955. Although the first publication of inventory theory can be found as early as 1886 by Edgeworth. The single echelon approach is based on considering a supply chain as consisting of individual stock points for which you have to set control policies, and these control policies for each individual item eventually lead to a control policy for the supply chain as a whole. So let's consider it step by step. So first of all, there's a procedure to apply the single echelon approach. As I said, each stock point is considered in isolation. Each stock point is related maybe to multiple items. So eventually we look at an item and a stock point in isolation. Then we have to set a service level target for this stock point, this item stock point that we want to achieve, to ensure that this item is available sufficiently for satisfying the needs from the customer, but in many cases it's not the customer, but what we call parent items, items that use the item to be assembled into, for example, or to be produced. The service level definition is important, but I'm not going to discuss this in detail. Then, of course, we need to gather data about the item demand. Typically, we will gather data over a period of, let's say, half a year or so, maybe longer, and we try to determine typically the mean demand per week or per day and the standard deviation of the demand per week or per day. Also, we gather data about the item supply process. Basically, it means that we want to figure out if we order the item to be made or to be purchased, then we measure the time between ordering the item and having it available to be used. That is what we call the item lead time or the item flow time. And again, we try to figure out what's the mean lead time and what's the standard deviation of this item supply lead time. And then, typically in a single echelon approach, we apply formulas from textbooks, or we can use the ERP system's safety stock setting procedure one way or another to determine the safety stocks or in general the control parameters of this item. And if you do this for each individual item in the supply chain, then we have our control policies, and you might say then we can start doing the planning, the ordering, etc. based on that. However, there are some caveats with this procedure, and I think it's important to know them. First of all, these stock points and items are not independent of each other, as they are related by bills of material. Even though we can use actual measurements to see, to take into account a child item and upstream items unavailability now and then, despite the setting of the safety stocks, we now and then miss an order. We can take that into account because that translates into a longer lead time than planned for, and that can be put into the data. However, if I need multiple items to be assembled, then this effect is not taken into account. And that implies that we usually, gathering the data on individual item basis, we might be too optimistic about the availability of the items for starting an assembly process. Another one is how to set these service level targets. It is still a trade-off to be made, but we do this for each individual item. We don't have an encompassing objective, nor do we have encompassing costs to take into account. So in fact, we don't make really a trade-off. There is a procedure to do so, but that would imply discrete event simulation, where you vary possibly thousands of variables. That's probably not feasible using discrete event simulation. The common way of doing so is just setting a service level target for ABC items, or just setting them 95% for all of them. So in that sense, it's a really heuristic. And another one that is important to realize is that the formulas from the textbooks to set those service levels that you're thinking of, that you measure in real life, are mostly either not in the book, or when the formulas are there, they're most of the time not correct. And that is the same for the formulas in the ERP systems. Now, that sounds a bit shocking maybe to you, but this is fact of life. This has been identified already 30 years ago. I was one of them being confronted with this as I was an internal consultant at Philips Electronics. I applied the textbook formulas, found out that they were not correct, and I just considered basic single-item, single-echelon situations. And that's basically where I found out that not the so-called models were wrong. The control policies were correct. However, the mathematics to calculate the right control policies, the right parameters, was more complicated than was suggested in the textbooks. And that is something that is still an issue that we struggle with the current ERP systems and also with the current textbooks. The math is even difficult if you consider the single echelon approach. So there are quite some caveats with applying this. Now let's turn to the so-called multi-echelon approach. Again, we consider a procedure, of course. Now, first of all, we do take into account in the multi-echelon approach the bill of material relations. Then what's the major difference between multi-echelon and single echelon is that we set service levels only for the end items, only for the items with demand that comes out of a marketplace that we don't control. That also implies that we can set service levels for spare parts with customer demand. Those spare parts typically have two sources of demand, namely when the parts are needed to assemble into a final product or module. And on top of that, we need those parts for servicing the maintenance of the products in the market with customers, users, consumers. Then we gather data about the item demand process, but only for these end items, in the same way we do a single echelon model. And we do the same for the item supply processes, although here we have to be careful. As we take into account explicitly the relationships between items, parent items and maybe multiple child items, in that case it implies that part of the uncertainty in supply on an individual item level, the fact that the child item is not available, has already been taken into account. So in this case, the supply process must be carefully measured, and you should measure it as when an item can be started to be produced or shipped, then we start counting time until it's replenished into the stock where we can use it for further purposes. That implies that we don't include waiting times for child items before we can start it, because that's embedded already in the model and in fact in the analysis of the multi-echelon approach. That makes this far simpler, although you have to be carefully measuring supply processes. And then we need a so-called multi-item multi-echelon solver to propose an optimal solution within the model. It cannot be anything else than advice. You should always check what comes out, but still. The caveats of this approach, there are always caveats, and that is that the MIME solver that is used may not propose the optimal solutions, as it turns out that at this moment in time, it's 2020 now, there are a few of these multi-item multi-echelon solvers that are effectively based on different mathematical assumptions that are not obvious to you. You might say those solvers ask you for the same data to fill out, although some of these multi-item, multi-echelon approaches also ask you to set service levels for all items. That already is an indication that that is not a real multi-echelon approach. But still, we know that there are various approaches that may not yield the right solution, and I can't help it. It also is caused by the great complexity of multi-item, multi-echelon model analysis, but still it's important to mention it. Now, there's what I call a great misunderstanding. I'll try to explain what I mean by it. As I said already, using a multi-echelon approach, using such a solver, that solver has to basically solve a very challenging, mathematically challenging problem, and we can only do so since about 2000, when a few alternative approaches were proposed. And you might say that, at least I know that the problem is not completely solved to the extent at least I would like to solve it because of this mathematical complexity. You might say that there's some hope that AI techniques might be of help, but it could well be that we have to proceed more in a mathematical direction than in a computer science direction to get the job done. However, the good news is that empirical research that I've been doing over these 20 years, since I also tried to develop a multi-item, multi-echelon approach. I've been testing this approach with a multitude of companies and basically finding that the multi-echelon optimization models were able to yield empirically valid models. And empirically valid means that I basically used historical data about inventory and about orders, yielding the average inventory for each item, the average order size for each item, and using that as a basis, together with the bill of material relationships, I could calculate customer service towards the customers of the supply chain, finding out that that was rather close to the actually measured service levels. That gave us some solid ground for saying, okay, let's move on and see if we can then also use such a multi-echelon approach for proposing optimal safety stocks, for example. And of course, still optimal only exists in the context of a model, but still we have been able to make steps to do so. But what is important to realize is the mathematics needed to solve these kind of things is beyond the capability of supply chain management professionals. And even if they're trained as engineers, and you might even say if they're trained as mathematics, having a master's degree, you need substantially more knowledge of probability theory and mathematical analysis to move on and understand the mathematics that is needed. But what is important, and this is part of the great misunderstanding, and there's a great misunderstanding that if I use a tool for inventory optimization or for finding my way from A to B, like in a navigation system, it is not necessary to understand the algorithms that do the job for you. And it's not coincidental that I mention navigation systems because we use them all, and we probably don't have a clue how they fix it in the software, but we use it because we can verify that it works. We get there more or less according to the time promised, and we take typically also the fastest route if we want it. So it is not interesting at all for people that are professionals in supply chain management or any other profession that they should know about how algorithms work. Another example would be Google's algorithm to search page rank, then we say, but we still don't know exactly, at least most of us, how that works. So it is not important. The only thing that matters is that you can judge the outcomes of the models. So if you use a tool like navigation systems or multi-echelon systems, you check whether the outcomes make sense to you. Could be that they not immediately make sense, and that's part of other presentations that I made available. that indeed multi-echelon starts showing you some results that are maybe not immediately logical to you, but still you can verify. If needed, you can be trained to start understanding what's going on. So the only thing that matters is outcome understanding. Another part of the great misunderstanding is that people say, maybe for the same reason I just mentioned, they say, we're not there yet. We first have to do single item, single echelon, and then we can do multi-echelon approaches. Now, I already indicated the caveats with single item, single echelon approach. So in fact, this argument is a bit strange. And my statement then is, you may not be up to it, but you're in the middle of it. Your supply chain is not even a chain, it's a network. And basically means you are in a multi-echelon situation. So you have to use multi-echelon tools to solve your problems. Now, in order to illustrate this a bit further, I would like to talk about a case study that we created. It's more a game. And I'll share with you the main findings. So maybe then for you the game is no longer interesting if you would like to play it. But it was all built based on the iPad Air. We gathered data about the iPad Air, about the components that are used for it, the distribution, but we only restricted to Western Europe distribution. We really carefully took into account data about the lead times that were needed to get components from suppliers in the part of the supply chain we considered. We also carefully looked at what time was needed to assemble things. And you basically see here now the structure of the supply chain. And here you see on the straight lines, those are the indications of the lead times in days needed to get various components. I'm not going to detail. I can provide you a reference where to find the case. This is here manufacturing of parts of the iPad Air, and then there's the final assembly of the iPad Air. Then this is European Distribution Center, and then this European Distribution Center backups. This one, OS, stands for online sales, but it also backs up RDCs, regional distribution centers in Poland, Italy, and the UK, in the Benelux, and these regional distribution centers, we have stylized it, they basically deliver to Poland, Italy, and UK, but you can imagine it will be in the region. But to keep the case not too complicated, we did it like that. And we said, okay, let's go for a target service level of 95%. We want that. And basically the assignment in the game is allocate inventory across the entire network so that total capital investment is minimized while still ensuring that service level is 95% for all of these end markets. And then we provide a tool, a multi-echelon optimization tool, but in this case we use it in the so-called evaluation mode, because we then the participants to the game have to set stock levels, average stock levels for all these stock points. And then we start the case with this single item, single echelon approach. And how do we start with that? We set the service level target 95, not only for the end market, but also for all stock points in the whole network. But what we do then is with those resulting average inventories from this single echelon approach, we can calculate, but then with a multi-echelon approach, what the actual service would be in the marketplace by setting those target service levels at 95%, because as I already indicated, the single item, single echelon approach is not capable of capturing, for example, the fact that things are assembled. And you see assembly here, assembly here, assembly here, but it also cannot capture easily the fact that now and then there's unavailability, and just setting 95% is a bit naive in order to think that you can then get everything right. And as we have the multi-echelon tool, we can check what is the outcome really of this single item, single echelon approach. Here you see the detailed data that we gathered for this case, but let's move on to the single item, single echelon solution, 95%, and here you get the user interface that we use. In the tool that we have, it's still a prototype tool, but it already has done a good job with many projects in companies. Here you see that we have a cockpit that says, well, this is the cost part, the tangible cost part, considering of capital cost, material cost, and then we have something called debt capital cost, and I'll explain that in a minute, and then the total annual cost. And here we see the stock on hand investment. So this is the investment part, stock on hand, debt stock, pipeline stock, and then total investment. And here you get the operational performance. And now it's important to note that you can see over here, we have set a fill rate target of 95%. Fill rate is the fraction of the amount satisfied from the shelf. With the single item, single echelon approach, we only have 92.7%. Now you can say, oh, not too bad. That's one of the mistakes people often make. You have to think more in terms of the back orders. We wanted 5% back orders, but we get about 8% back orders, which is about 50% more back orders than we really want. So that is still substantial. And on top of that, we see that the single item, single echelon approach has that stock. Now this indicated by this red rectangle, which is quite a substantial amount of investment, which you can see over here. And so we have about 4 million debt stock at the highest echelon. That's the echelon of items that we purchase. And there's some over here. And that stock I define as the stock that does not contribute to supply chain customer service. So I could just easily remove it, and there would nothing change in these numbers over here. Which basically means that if I remove it, I might have opportunity to get really the service level I want. However, the single item, single echelon approach is not helping you there, because it just tells you have to set stock levels like this. So the single item, single echelon approach creates dead stocks, useless stocks, and it also creates lower service than we intended to have, and that can be, of course, not the intention. So this has been then revealed, and now we can look at the multi-echelon approach. Here you see the allocation of the dead stock, but let's move on. Here is the optimal multi-echelon solution. And the optimal multi-echelon solution looks entirely different than the one proposed by the single item, single echelon approach, because you saw these indicate the investments in time. You saw investments all over the place at all levels in the supply chains. So this is the end item level, and this is the most upstream level, and here are intermediate levels. And basically what we see under an optimal solution, we reach the 95% service level, but also we see, and maybe you haven't seen it, we have now here an investment of about 8.6 million. In the single item, single echelon approach, we had 16.8, and we didn't even meet service level, because the stocks were entirely wrongly allocated in the supply chain. A bit scary, of course, is that you see that all these stock points over here doesn't seem to carry any inventory. That basically means that from inventory of purchase items, it seems that the inventory flows from that point into the point where it meets the customer. And this finding for this iPad Air case is not just for the iPad Air case. This is a typical finding, and this is discussed in some other presentations that I provide on the web. But this is then also the reason why we get substantially lower costs, because we put it at the right place, which is over here, close to the customer, the only place where you can provide service, and then we have a means to have a flow from purchase items, kind of converting in the right quantity to back up eventually the stock that's close to the customer. Now, this is the typical outcome, and this is impossible to be derived from the single item, single echelon approach, because of the service level setting of 95% for all items. Now, what you see over here is a decoupling stock of purchased items. There are a number of items that have long lead times, and I can show that in a minute, and that is now. You can see that in terms of value, there are two items. And I don't know exactly the abbreviation. We can look back in the presentation. But this item had a lead time of 114 days, costed, I think, about $14. So it was not per se cheap, but still, because of this very long lead time, you want to protect the downstream supply chain of this item against this very long lead time. Therefore, you put their inventory, and likewise, you do it over here, here, and here. All the big bars over here are bars that relate to end items. If you look to the this is in value. If you look in the picture in time, you see it's somewhat more pronounced. We basically put 5 days of inventory of this component. There's also here some inventory. And then again, the big bars relate to the inventory. And you see that with less than 8 days at all places, you should be able to reach out 95% fill rate in the supply chain, which is still not that much in terms of time.